Let's take a look at a surface generated by a rotation. And to keep things simple, we're just going to assume that our axis is the x-axis. So the axis of revolution is the x-axis right here. And also to keep things simple, let's assume that the curve is positive, it's in the positive y values. So it's above the axis of revolution. All right, and we made this very simple curve. It's parameterized from t is equal to a to t is equal to b. So it has parametric equations where t is between a and b, and we have parametric equations x of t, y of t. And we're assuming the usual caveats that these are nice and differentiable, nothing technically bad happens, like the derivatives are not both zero at the same time. A natural parameterization would work just fine for this purpose. Now, I want to know what the area of the surface of revolution is given by this curve. So first of all, what does that even look like? Well, if I were to revolve this around, grab a different color here. So we get a copy of it down here and rotate it around. We get this nice little surface. Here's the front side of that surface. And we no longer care about the volume, we only care about the surface area, front and back here. So in order to find this surface area, let's back up just a little bit. And in order to find the entire area, we're going to break it up into pieces. And each piece we'll call delta A, a piece of the entire area. And the piece should come from small chunks of the curve. So let's do that. Let's just take a small piece from here to here. And this is a straight line which has length delta s. Just like when you approximate the length of the curve itself, we break it up into tiny delta s's. Well, here's our delta s, and when we rotate that around, we get almost a cylindrical shell. It's not quite a cylindrical shell because of this slant here and here. In fact, let's take a drawing of this over here to the side. So we have kind of this slant here and here. But the good news is, because this delta s, we can assume it's so tiny that we can kind of fudge things a little bit, and we can assume that it's so tiny that it's basically straight up and down. Even if it was slanted just a little bit inwards, we can ignore that. All right, so now we've got this cylindrical shell, and I want to know the surface area on the front and on the back. All right, and what I could do is I could take advantage of the fact that I know the radius here. All right, the radius from here to here comes from this height from here to here, and that comes from a point on the curve. So we can just call that y of t. Again, we're assuming that y is always positive, so we don't have to take an absolute value around it. So the radius is equal to y of t, and the height right here, well, that was just given by the delta s. So the piece of the area, the delta A, would be 2 pi radius times the height. And that gets me, for each of these little pieces, 2 pi y of t delta s for the height. Okay, so I said it was equal, but that's a lie because this is just an approximation. So I should have just made that an approximation. To make this precise, we need to turn this into an integral. We limit these delta A's to be, and these delta S's to be as small as possible, infinitely small. All right, and so what do we get when we do that? All right, so A would equal the integral from, and we're going from t is a to b, of the area differential, of course. So that would equal, we can pull out this 2 pi if we want to the left here, 2 pi, and the summation becomes an integral from t is equal to a to t is equal to b of y of t delta S becomes ds when it becomes infinitely tiny. All right, so that's good. Oh, but I'm still integrating with respect to t, and I have, this is what we call the arc length differential. But when we investigated the length of a curve, we learned that ds is the same thing as, so we'll leave the y of t, but the ds can be replaced with the square root of dx dt squared plus dy dt squared dt. And so this is a nice short formula, but you have to expand out that ds into that square root dt. All right, so now we've got our area formula, and we will just use this blindly pretty much to solve the problems that we need to solve. Well, let's take a look at one of those. All right. Find the area of the surface of revolution obtained by rotating a portion of a parabola around the x-axis. All right, so let's see here. I can draw this picture. I'm not sure how much it'll help, but if I wanted to draw the picture, I could. All right, we're rotating around the x-axis. So here's my axis of rotation. And I know what that parabola looks like. It's the square root function. I'll sketch that from 0, 0 out to 4, 2. Okay. And it's being rotated around. So we get this sort of funnel shape right here, what we actually call an elliptical paraboloid. And we want to know the area of this particular surface. And all we need to know to figure that out, we don't have to draw the picture actually to solve this, because we have this nice formula. And because it's a very simple curve around the x-axis, we'll use the length is 2 pi integral from t is equal to a to t is equal to b of y of t square root dx dt dy dt dt. And again, all this is just from the ds, but that would be the expanded form. All right, we do have a moment to pause here because I have no clue what y of t is. I was given a function here, so I'm going to have to figure out what that function is when I parameterize it. Well, remember, we have a trick here. If you ever have a function, a curve defined by the function right here, the easy way to parameterize this is just let your x of t be t. It's that easy. And then your y, which used to be the square root of x, well, now it's the square root of t. So now I will take these, and I need to know what dx dt is. So my dx dt would be the derivative, which would be 1. My dy dt would be t to the 1/2, becomes t 1/2 t to the negative 1/2. All right, and so probably 1 over 2 root t would be the cleanest way to write that. So now we'll take this and we'll plug in to everything.